So today we're going to talk about proving space lower bounds for streaming algorithms. So we've already talked a little bit about this. We showed some linear lower bounds. Oh, you're scribing today, is that right? Okay, great. We showed linear lower bounds for several problems, both randomized and deterministic. But sometimes we want to we want to pin down like exactly the space complexity even for the randomized approximate algorithms, right? So we know that we can solve something in 1 over epsilon squared times log n space. Can we get 1 over epsilon plus log n space, right? So, you know, pinning it down exactly. So we're going to see some more sophisticated techniques today to prove space lower bounds, okay? And all the space lower bounds today are going to be via something called communication complexity. And I'll say what that is in a second. Okay. Anyone heard of communication complexity? Just out of curiosity. Okay. Good. And the problems we're going to look at today are F0, distinct elements. And the lower bound here is going to be 1 over epsilon squared plus log n bits. So we're going to show any streaming algorithm, one-pass streaming algorithm, which solves the number of distinct elements up to 1 plus epsilon factor, must use space 1 over epsilon squared plus log n bits. And after that, historically, after that lower bound was proven, we got an algorithm that actually matched that. So this is the optimal space complexity of distinct elements. We'll also see median, randomized exact median. So I'm not writing these in the order that I'm going to present in class. We're going to do median before F0 because the argument is simpler. And then we're going to also show FP for p bigger than 2 needs, so this here is going to need omega n. Okay, so if you can give the exact median of a stream in one pass with 2/3 success probability, that's going to require linear space. And FP for p bigger than 2, this is, remember, estimating the LP norm, well, to the p, let's say, up to 1 plus or minus epsilon. This is going to require n to the 1 minus 2 over p. Okay. And again, I believe it's, so in this case, the lower bound was proven first. That's right. And the upper bound was proven a few years later by Indick and Woodruff up to log factors. So anyone who 2 approximates FP needs at least this much space in bits. Okay. For this one, I'm not going to show the whole argument because it's more involved. But once you get to know what communication complexity is, I'll assert that a certain communication complexity problem is hard. There is a proof. I'm not going to do the proof in class. And then given that it's hard, we're going to show why it implies that this is true. Okay. So, good. I said via communication complexity. So what is communication complexity? Okay. So first let's look at 2-player communication complexity. Okay. So there's some Alice and there's some Bob. They each get, there's also a function which maps x by y into 0, 1, or true, false. Okay. So Alice secretly gets some little x in that set capital X, and Bob secretly gets some little y in that set, capital Y. And what they'd like to do is compute the function f. They want to compute f of xy. So Alice, let's say Alice is the one who starts the conversation. Alice will send some message, M1, to Bob. Okay. Bob will then get that message and then decide to send another message back to Alice, etc. And after some number of rounds of this conversation, someone will say, okay, given everything that's been said so far, I can determine that I can calculate f. And then that person will say, I declare that f is this. Okay? And the goal is to minimize, well, the goal for us today is going to be minimize the total amounts of communication. Or in other words, the sum of mi, where I goes from 1 to k. Where mi, by that I mean the length of the string mi. Let's say this is a binary string, so the total amount of information that was sent. Okay. Good. So there's always like some trivial protocol. Okay, so we're going to talk about communication protocols. A protocol is what a communication protocol is, some way of conversing that Alice and Bob agree on ahead of time. So Alice and Bob both know f, right? They both know what they want to be able to compute. They just don't know the other person's private input. So ahead of time, they're going to agree on a protocol, and they're going to say, okay, this is exactly how we're going to behave as a function of like the messages we've seen already and the private input that we have. Okay, and then they're going to start executing this conversation protocol, this communication protocol. And this is the goal. So there's always one protocol which is, there are two protocols which are kind of trivial and always work. One is that Alice just immediately sends the x to Bob, right? So how many bits does it take to send x to Bob? Log the size of capital X to describe an element of capital X. So that's always one trivial protocol. Another one is Bob will just send y to Alice. Okay, so they're always kind of two trivial protocols, and the goal really is to beat that, or sometimes to show that there is no non-trivial protocol. There is no protocol that does better than the trivial protocol. That's also going to be the kind of thing we'll show. Okay, make sense? Now, there's a natural. Let me stay on this board. There's a natural connection between communication complexity and kind of space lower bounds for streaming algorithms that works as follows. So suppose we had a communication complexity lower bound. I claim that a communication complexity lower bound can yield a streaming lower bound. Okay. And how is that? So there are different ways of measuring the complexity of a communication problem. Okay. So we'll restrict our attention to one-way protocols where Alice speaks. Okay. What do I mean by that? I mean, communication can only flow from Alice to Bob. We don't allow Bob to ever speak. In other words, Alice just sees her x and sends a message to Bob. Okay? So we don't allow this back and forth. Now, suppose we had a lower bound for some one-way communication problem. So Alice has some x. She has an x. Let me write it like this to be suggestive. Bob has some y. And we only allow Alice to send a message to Bob, at which point Bob has to then output the answer to the function, right? So the connection is, look, suppose I know I want f of xy. Okay. I'm going to start writing things and introduce notation as I write. Suppose we know a lower bound on the optimal complexity, on the optimal communication complexity. We call it D one-way f. Okay, so what I mean by this is what D of f is what's the cheapest communication protocol that solves f. So going back to this board, what's the protocol that minimizes this no matter what the input is? Minimize over the max input of this quantity. That's D of f. D arrow f means it's one way. So Alice can only speak to Bob. And D means deterministic. So their communication protocol is deterministic. So suppose that I know that, suppose that I know a lower bound on this thing, right? I know that no matter what one-way protocol you use, Alice needs to send at least this many bits, right? Well, we can do the thing we usually do, which is, well, if there's a streaming problem that can compute f for you, then Alice will view her x as a stream, right? She'll run the streaming algorithm on it, and then when she gets to the end of the stream, she'll send the memory contents of that streaming algorithm to Bob, who can then continue running the stream on y, and then he'll query the streaming algorithm and then get an answer, right? The total communication here was S, the space of the streaming algorithm. So here we have a protocol, a communication protocol that's using only S bits of space. But any protocol needs that many bits of space. Therefore, S is at least the one-way communication complexity of F. Okay, so I'm going to instantiate this with actual examples soon. But that's basically the connection. Yeah? What's Y? So essentially, what I imagine is going on here is that there's a stream, and the stream got cut in half, and the left half got given to Alice, and the right half got given to Bob, right? Okay. Good. So, yeah. Is f the function? Yeah. F is Okay. Well, let me instantiate this with an example, and then you'll see what I mean. Yeah, because you're saying often the outputs of our f's are not binary, right? So, but I'll show you an example to make this concrete in a second. So, let's go back to let's go to f0, the number of distinct elements. So we've already shown. Suppose we know. So we can basically get S-bit COM protocol. This is the space, which implies that S has to be at least D one way of F. Right? So let me instantiate this with an example. Exact deterministic F0, okay, requires omega n space. We saw this via compression argument very early in class a few weeks ago, but I just want to phrase basically an identical argument in the language of communication complexity, just so that you get used to arguing this way. So notice, as I said it here, we have to start with some communication problem that we know is hard. Okay? Start with a problem that we know you need a certain amount of communication to solve. And then what we're going to do is we're going to reduce that hard problem to our streaming problem. We're going to say that if you could solve the streaming problem, then you could solve that hard communication problem. Therefore, the streaming problem must be hard too. Reductions are a big thing in complexity. You've seen, I guess, NP hardness and things like that. It's the same principle. Okay, you reduce the hard problem to a problem, and then therefore that problem must also be hard. Okay, so we're going to do a reduction from the equality function. Okay, so equality is a function that takes two arguments, x and y. X and y are both bit strings of length n. And it's either 0 or 1. It's 0 if they're not equal. It's 1 if they're equal. Okay, that's the equality function. And claim the communication complexity of equality is omega n. We actually only care about the one-way communication complexity. But in fact, even if you allow conversation back and forth, it's still omega n bits. Okay. So I'm not going to prove this. If you think about it for the one-way protocols, it's pretty simple to prove, right? Basically, the way we proved the compression argument before, it's pigeonhole principle, right? So for one-way protocols, Alice just gets x and has to send a message. That's all and then Bob, based on that message, has to figure out whether x equals y or not, right? But so let's say that Alice sends an m-bit message, right? Well, unless m is at least n, there are two different bit strings that will yield the same message by pigeonhole, right? And then basically Bob will get one of them wrong, right? Let's say there are two inputs, x1 and x2, that by pigeonhole yield the same message. So if Alice has x1 versus x2, like she won't know which one Bob had, right? So one of those she'll get wrong, and then it won't be actually a correct protocol. So in fact, this thing actually has to be at least n anyway. We just proved it has to be at least n for one-way protocols, but it has to be omega n for no matter how much communication there is. Okay, so we know that any protocol for equality needs n bits of communication. Okay, so now we're going to reduce equality to f0. Okay, so suppose there exists an algorithm, a streaming algorithm for f0 using s bits of space. Okay. So Alice and Bob are here. Alice has her x. X is a binary string, an n-bit binary string. We're going to do the usual thing, where if xi is 1, she imagines that I is in the stream. And if xi is 0, it's not in the stream. She's going to run A. There exists an algorithm A. She's going to run this streaming algorithm A on her stream. She's going to send the memory contents to Bob. Okay? And then Bob is going to... Okay, actually, she's also going to send, let's say, Alice sends oh, yeah, okay, good. So Alice sends mem contents to Bob. Okay. And as soon as he gets it, he can basically Bob can just, this is really just a reformulation of the previous argument in terms of this communication reduction, right? So Bob can query f0 and know how many non-zero entries are in x. And then for I goes from 1 to n, he can append I to the stream and then see whether or not, and query f0 again and see whether it went up or not. And if it went up, that means that xi was 0. And if it didn't go up, that means xi was already 1. So you can recover what x is and then therefore determine whether or not it matches his y and solve the equality problem. But we know that any solution to equality requires n bits, so this message had to have at least n bits, so s is at least n. Okay. Questions? So we're going to see some more. It's the same argument. I'm just rephrasing it as a communication, or as a reduction from some communication problem. Yeah, there's nothing kind of under the hood. It's all the same argument, but the language of communication complexity is going to help us solve some harder problems very soon. So I wanted to be able to phrase what we did in the language of communication. Very good. So you've seen one example. Before we get into other examples, I want to define some terms and notation. So I already told you df is the optimal cost of a deterministic protocol. Right? We're also going to look at something I'll call R delta pub of f. This is, again, the optimal cost of a randomized protocol with failure probability delta, such that the random string is public. It's written in the sky. What do I mean by public? I mean, basically, Alice and Bob are actually deterministic people. But there's like an infinite random string written in the sky that both of them can see. Okay? And whenever they want to make a random choice, they'll look at that random string to help them make that random choice. But since it's public, kind of, I as Bob know the randomness that Alice has access to. So we can use that randomness collaboratively, right? No, so like for example, what we could say, remember the protocol is decided ahead of time, right? So Alice and Bob might say, okay, look, there's this random string in the sky. Alice is going to use the odd indexed random bits for her decisions, and Bob's going to use the even indexed ones, okay? So they're using different independent random bits, but the point is they know each other's random bits, right? So they don't have to, for example, they can use that to their advantage at some point to have even cheaper communication, because they know something. If you think about those random bits as being their private inputs, they know something about their private input, right? They know what that random string was anyway. I know what randomness Alice is using, and Bob knows what. Well, they can do whatever they want, right? So there's this random string they know is in the sky. If they want, they can ahead of time split up and say, use the odds, I'll use the evens. Or they could say, we'll both use random bit 5 at index 5 to do something together, right? They can do whatever they want. There's also R delta private, which is similar, but each of Alice and Bob have a private random string. And then there's also what I'll call the distributional complexity. This is the optimal cost of deterministic protocol with failure probability delta when the pair xy is drawn according to the distribution mu. So this is called the distributional complexity. You imagine the input's actually random. Okay. Questions about any of these definitions? Okay. So I'll assert something. So claim df is always at least the private communication complexity. Is always at least the public. Is always at least d mu. Okay. Remember, this measures the best protocol, like the cost of the best protocol. So like this one is pretty simple, right? So look, if Alice and Bob have access to private random strings, they can just choose to not use them and just be deterministic. So any deterministic protocol can be simulated in the private coin model, right? Therefore, you can only do better by having access to the private coins. So that's this inequality. This one, look, so you can do what I said. Ahead of time, Alice will say she'll use the even indexed random bits in the sky, and Bob says he'll use the odd indexed random bits in the sky. From then on, they just simulate now the private coin communication protocol. So that's this inequality. This one is basically by an averaging argument. Essentially, what we know is, what does this mean? This means that, for all xy, the probability over the random string s that, let's say the protocol, let's call the protocol pi, or let's call the protocol p, the probability the protocol is correct is at least 1 minus delta. But that implies that, since it's true for all xy, it's true for a random xy. So the probability over xy coming from mu of the probability over the randomness, let me call it PS. PS is the protocol when it's fed randomness S. That PS correct is at least 1 minus delta. And then now you just switch the order of the probabilities. So this implies that the probability over S, the probability over xy coming from mu, that PS correct is at least 1 minus delta. But if for a random S, this probability is at least 1 minus delta, that implies that there exists an S for which this thing is at least 1 minus delta. So this implies that there exists an S such that is at least 1 minus delta. So let's call it S star. There exists an S star such that, so that implies, so PS star is a deterministic protocol. Implies that d of mu delta of f is at most the cost of p star. Yep. Does that make sense? I just switched the order of these. So if the probability over S of this thing being large, if a random S has this thing being large, has this probability being large, that means there exists an S where this thing is large. Okay. Yeah. S is the randomness. So what do we know? So what I'm saying is that there is a protocol. So what is it? What is R delta pub F? It's the cost of the best randomized protocol, right? With public randomness. So call that protocol P. P is using some public random string, which I'm calling S. And what I'm saying is I can now use P to come up with a good deterministic protocol for the distribution mu. And that's what this is doing. So I know that for all, basically what I establish is that for a random draw from mu, a random protocol PS works with good probability. Once you fix S, PS is a deterministic protocol. PS is the protocol P if you fix the random string to be S. Right? So, and then I reversed those inequalities and I said, look, that means that for a random protocol, it works with high probability. So if a random protocol works with high probability, that means there exists a protocol that works with high probability. Oh, I mean, these are just different ways of defining the communication complexity of a function f, right? So d mu delta is just one way of defining the complexity. It's the complexity under distribution mu. So this inequality holds no matter what mu was. It holds for all mu. But of course, S star will depend on mu. There exists an S star, which is a function of mu. But okay. So if we want lower bounds against deterministic streaming algorithms, we'll usually want to lower bound df, which is easier because df is the biggest of them all. If we want to lower bound randomized streaming algorithms, okay, so which of these most naturally fits randomized streaming algorithms in your mind? Is it distributional? Is it public coin? Is it private? Seems like, why public? Okay, so Alice gets half the stream and Bob gets the other half, right? Alice is going to send the memory contents to Bob, right? So for Bob to, in a lot of these streaming algorithms, there are some hash functions that are being defined. And those hash functions, they don't live in the sky, right? You have to actually pay to store the hash function. So in order for Bob to continue running the algorithm, he needs to know what the randomness was in your hashing. Right? That's not communicated for free to him. Right? So really the thing that models most closely what we care about is private randomness. So what we want to lower bound when we deal with randomized streaming algorithms is the second one, the private communication complexity, the randomized communication complexity with private coins. Question? Oh, just because a randomized streaming algorithm needs to actually know, your randomized algorithm, let's say you're looking at, distinct elements or whatever, these randomized algorithms we've been looking at, right? Where's the randomness coming from? It's coming from some hash functions that the algorithm is computing, right? So in this example where Alice runs the algorithm on her input, then sends it over to Bob, Bob had better also know the hash function that Alice is using. Otherwise, he can't continue running the algorithm properly. It's not public, though, right? That hash function is not public in the sense that Bob just doesn't know it, right? Basically, to continue running, so let's say that I ran my count min sketch algorithm, right? Which is all about hashing. So count min had this grid of counters. I had half the stream. After half the stream, some of these counters have numbers in them. Now you're Bob. I send you these counters, and then you have the second half of the stream, and you're supposed to continue running the algorithm. Yeah, you need the hash functions. So the hash function is not written in the sky. I need to actually tell it to you. Yeah. Right. All the description of the randomness that Alice is using needs to be communicated to Bob for Bob to be able to continue running the algorithm. So we're going to model that as private randomness. It needs to be included in the space that's sent, right? So that's for us private randomness. Okay. Now, even though private randomness most naturally models what we care about, we're often going to lower bound the public communication complexity because private is at least public. So if we lower bound public, that will be a valid lower bound for private. And in fact, often the way we're going to lower bound the public communication complexity is to lower bound the distributional. Okay, so we're going to come up with a hard distribution, mu, because this lower bound holds no matter what mu is. So we might as well make it as hard as possible by making mu to be as hard as possible. So we're going to cook up a hard distribution mu, oftentimes, and then show a lower bound on the distributional. And that will imply a lower bound on the private, which will imply a lower bound on the streaming algorithm space complexity. Does that make sense? So if you want to learn more about this stuff, I recommend there's a book. It's an older book. There are some more recent surveys as well, but there's a book by, it's called Communication Complexity. Okay. And it's by Kushi-Levitz and Nissan. And, there's some interesting things with communication. So for example, we saw that dEc is omega n. Anyone have an idea of what R pub of ec might be? Well, I'll just tell you, it's a hard thing to just come up if you've never seen this before. It's constant. You can actually solve equality with public randomness in a constant number of bits. Let's say that delta is a third. Okay. And the private communication complexity of equality, private coin, is log n. Basically, what you do is Alice picks a random prime, and then a random prime which is at most n cubed or something. And then she sends x mod p as well as the prime itself. Okay. And Bob then can compute x minus y mod p because he knows the prime and he knows x mod p, right? And if they're actually different, then a random prime would witness that difference with good probability if you pick the prime big enough. And actually, both of these things are optimal. It really is constant for public, and it really is log n for private. There are matching lower bounds. And in fact, this gap of log n is the worst possible example. So there's something called Newman's theorem, which says that so you can basically reverse that middle inequality at the cost of an additive log n. The private coin complexity is always at most the public coin complexity plus log n. So there's some very non-trivial and interesting things going on there. I'm not, this is not a class on communication complexity. I just want to get you familiar enough with it that you can use it for some problems that are relevant to us. Okay. Yeah, that's right. For equality. And I'm imagining delta is a constant, like a third or something. Okay. So now, in order to get some of the other things I wanted to show you, like this 1 over epsilon squared bit lower bound for f0 and this median lower bound, I'm going to need to get into a problem, a communication problem called index. We're going to show that index is hard for one-way protocols. Okay? And then we're going to reduce index to some other. We're going to reduce index to median. So this is. Let me now show you the map. So first of all, we're going to show that index reduces to something called gap hamming. I'm just giving you a map of where we're going. And then gap hamming is going to reduce to f0. And we're also going to show that index reduces to median. And we're also going to define another thing called disjointness. Okay. So T-player set disjointness. So far we've just been talking about communication complexity with 2 players. You could imagine having T-players where each one has their own private input, and then the first player speaks to the second, who then speaks to the next third, who then speaks to the fourth, et cetera. And finally, the last player, at least in one-way protocols, the last player has to then output f of all the inputs. Okay? So that's T-player one-way protocols. Okay? We're going to show that there's a problem called disjointness with t players, where t is appropriately chosen, such that that thing reduces to fp for p bigger than 2. And we're gonna do it where in this reduction t is going to be something 2n to the 1 over p. So this is a map of the rest of the lecture, okay? I'm going to define what index is for you, and what disjointness is, etc. And this is just today, but actually, I mean, index has been used for probably dozens of streaming lower bounds in the literature. Okay, so it's a very canonical hard problem. When you deal with NP hardness, think like 3-sat, right? You often try and reduce from 3-sat, and it's a very simple problem. So index, it's a 2-player problem. So Alice, she gets some x, which is in 0, 1 to the n. And Bob gets some j, which is between 1 and n. And index of xj is x sub j. Okay? And the claim is that the public delta complexity index is at least 1 minus h2 delta n, where h2 is the binary entropy function. So h2 delta is defined to be delta log delta plus 1 minus delta log 1 minus delta. Okay. So as long as so I'm not going to, you can plot this function if you'd like, but the point of this function is as long as delta is significantly larger than a half, or sorry, significantly less than a half, delta is the failure probability. So let's say delta is a third. This thing is some constant. Okay. When you move toward a half, it then becomes I guess, move towards 1. Okay. Yeah, h2. So h2 of delta, it's called the binary entropy function, and this is the definition. So if delta is like a third, h2 of delta is some constant that's less than 1. So 1 minus it is some constant. So this is linear lower bound. Okay. In fact, it's even true that the distributional complexity of this problem, where mu is the uniform distribution. Okay, so Alice gets a random string, and Bob gets a random index. Even that thing has the same lower bound. Okay. Yeah. Question. Yeah. Sorry. So pub one way. Yeah. So if it's not a one-way protocol, there's a trivial thing, which is Bob can just send his input to Alice. That takes log n bits. And now Alice knows the answer because she knows the entire string x. The reason it's hard is because it's one way. Alice has her input, and she has no idea what index Bob cares about. She can try sending a random subset of her bits, but for that random subset to contain Bob's index, if Bob is like a random index, you need to basically send most of your indices, right? So. Log base 2. Yeah, that's right. Log base 2. LG is log base 2 for me right now. Sorry. Yeah, okay, so so it's log base 2 for now. Yeah, sorry about that. Okay, so it's a lower bound you might not be surprised by. Makes sense, right? It basically says Alice can't do any better than sending her whole string. Okay, so we're going to prove this lower bound. But before I prove it, I'm going to have to give a little information theory crash course. I'm not going to prove much. I'm just going to like define things and then state things. If you want to learn more, there's a book by Cover and Thomas, which is called like The Essentials of Information Theory or something. I might be getting it slightly wrong, but if you Google Cover and Thomas, I'm sure you'll find the book easily. If you want to learn more about this, or take you can find some lecture notes, etc. So, some definitions. So, if we have a random variable x, I'm going to say that the entropy of x, h of x is the Shannon entropy, is the sum over x. The probability, so p little x means the probability that capital X equals little x times log of, let me put a minus sign here, log p of x. This is log base 2, sorry, for any confusion. So this is equals the negative of that. So if you have two variables, h of x, y, then really what I'm looking at this is a joint distribution over xy, right? So this would be negative the sum over xy, pxy log of pxy. I also want to define for you what's called a conditional entropy. This is just the expectation over y of the entropy of x given that y is equal to little y. Okay. And what other definitions do I want to give you? There's also the mutual information. Which is equal to h of x minus h of x given y, which happens to be the same thing as the information between y and x. Okay, so entropy, conditional entropy, mutual information. Okay, so I'll just say maybe a little bit. So let's say that, okay, so let's look at the support of x. Let's say that x is, let's look at the support of x. Let's say x is a discrete random variable. Okay. How many people have seen all these definitions? Okay, so some not. Okay, so I'll just say, spend a minute. Basically, look at the support of this distribution, of this random variable. The entropy is like if you're trying to minimize the expected encoding length of specifying, an event that happened in or the value of the random variable x, what's like the expectation of the length of the message you need to send to specify what event happened. Okay, that's one way of interpreting entropy. I'm not going to justify that statement, but it's achieved by, for example, like Huffman coding. And then mutual information is basically telling you, how much of the randomness of x is revealed to you if you know y. That's sort of the intuitive meaning of it. Okay, so for example, if x is just a function of y, these are not independent random variables necessarily, right? If x is just a function of y, then y tells you all the information you need to know about x. If you know y, you know everything about x. So therefore, the mutual information in that case should be the entropy of x. You know all the randomness of x. And indeed it is, because the entropy of x is here, and then you subtract the entropy of x given y. But if x is just a function of y, then there is no entropy left in x once you know y. So this is 0. Okay. Anyway, so I just wanted to say those things so you have some sense of what these things sort of mean. And there are some basic lemmas concerning these quantities. which I won't prove, but we'll use them. There's the chain rule. Which says that h of xy is equal to h of x plus h of y given x. And there's also the chain rule for information, which says that the information between x and y, if you're given z, conditioned on z, is the same as the information of x between x and z plus the information between y and z given x. Okay. There's also subadditivity, which says that h of xy is at most h of x plus h of y. Right? The amount of randomness in this pair of random variables is at most the sum of the randomness in each of them. And this is an equality if and only if x and y are independent. If x and y are independent, then you really are separately learning the information in x and the information in y. But if there's some correlation, then there's less randomness in their joint distribution. Okay. And you can also get, these two things, chain plus subadditivity, imply that. Oh, okay. Well, this is. I guess this makes sense intuitively. Again, not doing the math, but just going with intuition about entropy capturing how much information is in the random variable. Well, if you condition on anything, basically the amount of randomness can't go up. Okay, that's what this inequality says. Also, let me write two more things. H of x is always at most log the size of x, log the size of the support of x. And equality is achieved by the uniform distribution. Okay. Also, h of x. I'm sorry? This one? This one is at most. X might have no entropy, right? Like if x is always 1, it has no entropy, even though, and it's like, it's 2 through n with probability 0. Also, h of f of x is at most h of x for any function f. And the last thing I want to write is something called Thanos Inequality. So Thanos Inequality is basically, let me say it in words before I tell you the actual inequality. What Thanos Inequality says is, okay, there's a random variable x, and there's a random variable y. Suppose I only gave you y. You're some prediction algorithm. All you have is y. You don't have x. And based on y, you make a guess for what you think x is. Okay? Then if your guess is good if there is a way to estimate what x is with good probability, it implies that there's like a lot of correlation between y and x, right? So what it says is that the conditional entropy of x given y can't be that big. So Thanos Inequality says that if, for two random variables, they're not necessarily independent. The interesting case is when they're not independent. For two random variables x, y, if there exists a predicting algorithm, G can even be randomized, such that the probability that G of y is not equal to x is at most delta, then there can't be too much entropy left in x conditioned on y. Okay, the entropy of x given y is at most the binary entropy of delta plus delta times log base 2 of the support size of x minus 1. Usually, when we invoke Thanos inequality in a second, when we're proving lower bounds for index, we're going to be dealing with random variables that are binary. So this is going to be 2. 2 minus 1 is 1. Log base 2 of 1 is 0. So this term won't really matter. So what we're going to say is that the conditional entropy is going to be at most H2 of delta. Okay. I think I forgot a minus sign. Yeah. Good. So if you think of delta, negative log delta is the same as log 1 over delta. So if you think of delta as being very small, this is basically delta times log 1 over delta, which the log 1 over delta grows much, much more slowly than 1 over delta does. So this is basically, think of it as like delta, morally, okay? So this thing is basically, for small delta, it's like delta. It's like delta log 1 over delta. So if you're able to predict with good, if you're able to predict such that your failure probability is at most delta, the conditional entropy is at most delta times log 1 over delta. Okay? That's Thanos inequality. Questions? Okay, so now we're going to go back to indexing. We want to prove that lower bound I said, that claim that I said over there. So let pi be the transcript of the communication protocol. So in this case, it's a one-way protocol. So the transcript, by the transcript, I just mean the history, the log history of like who said what when. Okay. In a one-way protocol, the transcript is just a single string. It's just what did Alice send. There's no back and forth. So when I put this arrow, I mean it's one way. So only Alice speaks, and then Bob has to declare an answer. Yeah, if it's two-way, Bob can just tell J, and that takes log n bits, right? So this is not a hard problem for two-way protocols. It's only hard for one-way protocols. So good. So we know that. So let pi be the transcript of the communication protocol of the, let's say, of the optimal communication protocol for the problem. So pi is the thing that actually achieves the optimal cost. So we know that R delta pub index is equal to the length of pi. Okay. Which is at least the entropy of pi. Which is at least the mutual information between pi and, say, the input. Which is the same thing as the mutual information between the input and pi. Right? So here, I mean, by the input, I mean the input to Alice and Bob. So the string x as well as j. This is equality. Yeah, there's no difference. You mean this line and this line? This is the mutual information between pi and the input versus between input and pi. But those two things are equal. Yeah, yeah. Okay. So what do we know? We know that for all x, that Alice is getting, the probability over the random string in the sky that Bob's output is correct is at least 1 minus delta. Okay. Which implies that, if you take a random x, this is a uniformly random x, then the probability that Bob's output is correct is at least 1 minus delta. Okay. So Bob is basically, let's call this now capital X. This is a random variable. Bob is basically G, right? What does Bob have access to? He has access to Y. Y is the transcript of the protocol. And just given the transcript of the protocol, he's able to predict what the jth bit of X was. Okay. So, actually, I should have said it like this. Right. So I guess what I should say is, I should have put a line in here which says, okay, let me put it like this. So this implies for all x and for all j, for all x and for all j, sorry. Bob's output is correct with probably at least 1 minus delta. So for a random x, so for all j for a random x, he's able to correct it. He's able to guess xj. So this implies that for all j by Fano, the conditional entropy of xj, given the transcript, is at most h2 delta. Right? So in a general protocol, pi is a sequence of strings. The first string is what was Alice's first message. The next string is what was Bob's first message. The next string is what was Alice's second message, etc. For us, pi is just now a single message because it's a one-way protocol. Pi is just what's the message that Alice sent. Yeah, it's a sequence of zeros and ones. That's right. Yeah, so let's say that pi always sends the same number of bits. Yeah, because since we're measuring the cost of a protocol by the worst amount of communication it ever sends, we might as well, if it ever wants to send less than that, just pad it so that it sends exactly that. So, yeah. Yeah, so pi is a random variable because there's a random string in the sky, right? Pi is a random variable because there's a random string in the sky. So what Alice sends depends on that randomness. And then here, here I switched to the case where capital X is now itself also random. So pi also is random in that it depends on X. Okay. Very good. Okay, so now let's start arguing. Okay, so good. So what we had before was that the length of pi is at least the mutual information between x and n pi. Okay, and then we're going to use the chain rule. This is the sum over all I from 1 to n of the information of xi and pi given everything that came before it, right? That's the chain rule. I'll just call this like x less than I. So I did the chain rule basically n minus 1 times. Okay. And then I'm going to write down the definition of mutual information. This is the sum over all I of the entropy of xi given this thingy minus the entropy of xi given pi and this. Okay. What's this number? It's 1. Right? If x is a uniformly random string, then xi is independent of all the xj's before it. So this is the same thing. This is the same thing as h of xi, which is 1. Right? And this thing, right? Well, we have this inequality which says that conditioning can only lose you entropy. If you condition on anything, you can only lose entropy. So this thing is at most h of xi given pi. But by Thanos inequality, we know that that thing is at most h2 of delta. So this whole sum is at most, or at least, sorry. Yeah, so this quantity is at most h2 of delta, which means minus this quantity is at least h2 of delta, or is at least minus h2 of delta. So this whole thing is at least n times 1 minus h2 of delta. Where did the? Oh, because I'm summing from I equals 1 to n. And each summand is at least 1 minus h2 of delta. Okay, so now that we have indexing, let's use it to prove another lower bound. So example problem, median. So we have a stream, let's call it x1 up to xn. For all I, xi is in the range from 1 to m. And we're looking at streaming algorithms here, and we want to know what's the, let's look at randomized exact median computation. So compute the median of this input x1 up to xn with probability at least 1 minus delta. So I want to show you now a reduction from indexing to median. So if we could actually solve median, that means we can solve indexing, so there's a lower bound for median. So claim index on 0, 1 to the n reduces to median with m being something like 2n plus 2, and stream length, 2n minus 1 or something like that. Okay. So remember now, Alice, we have to do a reduction, right? So Alice, so let's do the proof now. Alice gets some x and 0, 1 to the n, and then Bob just gets a j from 1 to n, and he wants to know what xj is. Okay. So Alice has to create a stream, run the median algorithm on her stream, send the memory contents, and then Bob now then will append some stuff to the stream and then ask what's the median. Alice inserts 2 plus x1, 4 plus x2, 6 plus x3, etc. into the stream. And then Bob inserts, I believe the right, I'm always tend to get off by ones on this, so I think n minus j minus 1 copies of 0, and another j copies of 2n plus 2. So let me just draw a little picture. Right, so here's 2, 3, 4, 5, 6, 7. Let me get rid of this. 2, 3, 4, 5, 6, 7. So let's say that n is 3. Alice inserts, so Alice, let's say Alice has 1, 0, 1. So she's going to insert into the stream 1, 0, 1. Or let me put 7 next to 6. So kind of from each pair, she'll pick the element of the pair that corresponds to her bit and put that in the stream. Okay? Does that make sense? So she'll insert 2 plus 1, and then 4 plus 0, and then 6 plus 1, because she has 1, 0, 1. And then now, Bob actually cares about a particular index, like the first index. I think, by the way, I might be off by ones here. We'll see in a second. But the point is, Bob wants a particular index. So this stream has length 3 right now. What he's going to do is he's going to make this stream be length 5, such that the index he wants is exactly in the middle. So if you want this guy to be exactly in the middle, what you should do is you should add 2 zeros to the beginning of the stream. Well, I mean, he's going to add it to the end of the stream, but the median is of the whole set, right? So he's going to add 0 twice to the set. 0 is less than everyone. So basically what he's doing is he's shifting over this guy to be closer to the middle of the sorted order. And then he's going to ask what the median is. And based on whether the median is this or this, he knows which bit it was. Right? And if he wanted a guy who was closer to the end, he won't put the zeros here. He'll put 2n plus 2s here. And now this guy's in the middle. And basically, by balancing how many zeros he puts on the left and how many 2n plus 2s he puts on the right, he can make the median be whoever he wants, and then get the index that he cares about. That's it. That's the proof. Okay. Since we're running low on time, I'll put a pointer to a proof in the notes for gap hamming. And so remember, I also said that index reduces to gap hamming, which reduces to f0. I'll put a pointer to that in the notes, okay? And then I'll show you this right now. So what's gap hamming? Let me define the problem. So the gap hamming problem gets 0, 1 to the n, and gets x and 0, 1 to the n, and then Bob gets y in 0, 1 to the n. And there's a promise. This is a promise problem. They're promised either the Hamming distance between x and y is bigger than n over 2 plus root n, or it's less than n over 2 minus root n. And they have to decide which. So, one way you can show that gap hamming has high communication complexity in the one-way model is to reduce from a problem that's hard in the one-way model, like indexing. And in fact, such a reduction exists. So you can look at, for example, I'll put the link in the notes, but Jairam Kumar and Shiva Kumar in, I believe, 2008 showed that index reduces to gap hamming. They were not, so this implies that our pub, let's say a third, one way of gap hamming is omega n. So the communication complexity of gap hamming in the one-way model is omega n. They were not the first to show this. So actually, there are previous papers of Indick and Woodruff who got this result, but they did a clean reduction from indexing. Okay. Later, after them, it was shown that even if you allow yourself an arbitrary number of rounds, you still need linear communication for gap hamming. That was actually an open problem for several years. And then Chakrabarty and Regev showed that even with multiple rounds of communication, you still need omega n. We're not going to get into that. But good. So let's say now we know gap hamming is hard. And actually, okay, let's do this. So claim failure probability 1/3 for 1 plus epsilon approximate f0 requires space omega 1 over epsilon squared. How would you prove that? Proof will reduce from gap hamming okay, so this is going to be assuming 1 over epsilon squared is less than n. Of course, you're never going to get a lower bound better than n. Reduce from gap hamming. So Alice, Bob get xy in 0, 1 to the t. So we're going to reduce from gap hamming, where they each get t-bit vectors, where t is something like theta 1 over epsilon squared. Okay. And now we're going to do the usual thing. If there's a 1 in Alice's input, she's going to include I in the stream. And if it's a 0, she's not going to include I in the stream. She's going to send that to Bob. Bob is then going to continue running the algorithm. And then he's going to, based on that, determine whether we're in this case or this case, whether it's at least t over 2 plus root t or t over 2 minus root t. Notice in this case, so this implies that kind of t over 2 minus, actually, let's say there's some constant here, some small constant. So it's t over 2 minus epsilon t versus t over 2 plus epsilon t. Right? Because by our choice of t being 1 over epsilon squared, root t is basically the same thing as epsilon t. Okay. Notice that f0, twice f0 is equal to the weight, or let's call it like the support size of x plus the support size of y plus the Hamming distance between x and y. Why is this the case? Well, let's look at each index one by one between 1 and n. If I is both in the support of x and the support of y, then it will be counted twice here. But it won't be counted here. So it'll be counted twice, but it'll only be counted once by f0. So we put the 2 there to make sure it's counted twice on the left. What if it's only in one of the supports but not the other? So if it's in this support, we count it here. We won't count it here, and we'll count it again in the Hamming distance. So it'll get counted twice here as well. Whereas again, it'll only get counted once here. So we put this 2 here. So this is just an equality. Okay. So Alice, basically out of time, I'll wrap this up. I'll move on to disjointness in the beginning of next lecture, but let me just finish this. So the point is, Alice sends streaming contents, streaming memory, and the weight of her vector x. This is a total of s plus log t bits. Alice sends s plus log t bits, right? Now Bob, he knows an approximate f0. He knows the support of x because she sent it. He knows the support of y because he knows y, right? So Bob knows, he knows 2 times 1 plus minus epsilon f0, which is the same thing as 2f0 plus or minus, at most, epsilon t. Let's say he even does an epsilon over 2 approximation. Okay. And so he estimates the Hamming distance as being, whatever it should be. So 2f0 plus or minus epsilon over 2t. This is the approximation he gets from the algorithm minus the support of x minus the support of y. This is estimate, which is the truth plus or minus epsilon over 2t. So based on this information, he knows the actual Hamming distance up to this error, so he can decide that problem. Okay? Therefore, you need 1 over epsilon squared bits. I didn't get to show you the additional log n, and I didn't get to show you the final thing over here. I'll say that at the beginning of next lecture. And then starting next week, we're going to do some dimensionality reduction and move out of, well, it's going to be related to streaming, as you'll see, but it's going to be a different topic. Okay? And I think the p-sets due Monday.